Welcome to Vector Calculus, and today we are going to teach you about the fundamental theorem of line integrals.
The history of fundamental theorem of line integral is also known as gradient theorem. The theorem says that a line integral to gradient field can be evaluated by evaluating original field at the endpoint of curve. The ancient Greek mathematicians knew how to compute the area via infinitesimal, and we call the operation as integration. This term relates the differentiation and integration because they are essentially inverse of one another. In mathematics, an integral assigns numbers to functions in a way that can describe displacement, area, volume, and other concepts that arise by combining infinitesimal data.
The people who introduced this theorem, one of them is James Gregory, who was the first to provide the published statement and the proof of rudimentary form of theorem with a strong geometric mechanics. However, Isaac Barrow is the one who proved the more generalized version of this theorem. But in the further future, Isaac Newton had completed this development of surrounding mathematical theorem, and Gottfried Leibniz also had systemized the knowledge into a calculus for infinitesimal quantities and introduced the notation that we have used today. And finally, Bernhard Riemann was the one who gave a rigorous mathematical definition of the integral.
Bernhard Riemann gave a definition based on a limiting procedure which approximates the area of curvilinear region by breaking the region into thin vertical slabs. During 19th century, more sophisticated notions of integrals began to appear. The type of function as well as the domain over which integration is performed has been generalized. A line integral is defined for a function of the 2 or 3 variables, and the interval of integration AB is replaced by a certain curve connecting 2 points on the plane or in the space. Okay, we want to derive operator. Here it goes. First, we want to integrate the dot product of vector function f and dr. We need to assume r equally to x and y. So, the derivative of the r equally the x and the y. And next, vector function f consists of f and g. Then, we need to put it together and be like this.
I will explain a few examples and application of fundamental theorem of line integral. The question is, evaluate integral of f dr where f xy equal to x y square I plus x square yj, and the path c, which is c is the curve, is a parabolic given by y equal to x square. This is the function, and then given two coordinates, which is p and q. P is 1, 1 and Q is 0, 0. So to solve this question, we have to just input into the formula, which is integral of f dr. First step is we have to let x equal to t and y equal to t square to standardize the function in terms of t. And then find the first value, which is r, xy. R is xi plus yj given. Standardize it into one term, which is t, into ti plus t square j. From r function, we have to differentiate to get the r, and then it turns into I plus 2tj dt, and then input into the main formula, which is integral of f dr, and then it becomes integral of lower limit from 1 to 0 x y square y dot r dt. And then from this, you can solve it by change the limit, and then you have to add minus, do dot product to get this value, and then just integrate to get final answer, which is negative 1 over 2. Okay, next question is question 2. Okay, the question is evaluate integral of f dr where f xy equal to cos xi plus sin xj, and the path c is the oriented curve rt negative pi over 2i plus tj, and the value of t is given, which is not more than 2 and less than 1. Okay, this is the curve, which is rt, and it is given in the question, that one, RT. And then from RT, you have to differentiate it to get the R, which result in 0i plus j dt. Just input into the main formula, which is f dr, to get the area below the curve. F is given, which is cos xi plus sin sj. Cos xi plus sin xj. Substitute value of x, which is negative pi over 2, and then the product with 0 and 1, which result in integral of 0 plus negative 1 times 1, lower limit 1 and 2. Then after we integrate, final answer is negative 1.
Okay, my name is Afiq and I'll proceed with example 3. So, the question asking us to find f where it is given that 3 plus 2xy, x squared minus 3y squared equals to del f. So, the solution is we divide the equation into two parts where 3 plus 2xy equals to 2p and x squared minus 3y squared equals to q. And for p part, we differentiate in terms of y, where we will get 2x, and for the q part, we differentiate in terms of x and we'll get 2x. And it is proven that delta p over delta y equals to delta q over delta x, where we know that f is exists. So to find the solution, to find f, we need to integrate fx and fy, where fx equals to delta p over delta y and fy equals to delta q over delta x. So when we integrate fx, we'll get this answer, where 3x plus x squared y plus constant function gy, and when we integrate fy, we will get x squared y minus y cubed plus constant function hx. Make it the both equation as equation 1 and equation 2. After that, with equating both equation 1 and equation 2, and basically we can cut off both sides x squared y and x squared y, and compare both equation. We will get gy equals to negative y cubed and hx equals to 3x. For gy and hx, we substitute back to the equation 1 and equation 2. We'll get the final answer f equals to 3x plus x squared y minus y cubed. That's all.